Okay, so this video is about the transition from studying the spacetime algebra, especially in terms of electromagnetism and special relativity, to studying general relativity. And incorporating that into the spacetime algebra as a means of bridging understanding of what happens in a curved spacetime to what is happening at the quantum scale. And so the place I'm choosing to begin with general relativity is the energy momentum tensor, which is an ambitious way to begin because, well, for one thing, when it comes to general relativity, the concept that is most difficult to find information about is the energy momentum tensor. There certainly is writing about it, a body of knowledge about it, but it is smaller and more difficult to locate on the internet. But what this tensor is a mathematical object that has 16 inputs, a system of equations, a system of functions that where the inputs are energy density, momentum density, energy flux, quantities of pressure and shear stress. And the output of these functions, organized into the energy momentum tensor, is spacetime curvature. And, energy density arises from time. And then the other quantities arise from comparisons between time and space. These are third degree partial derivatives because we are making comparisons of change in time versus three different directions at once versus change in these three directions compared to each other and to time. It's a combination of comparing one parameter to the other three. And then once a value is obtained for each input, we multiply times a factor of 4 pi and the gravitational constant. And what that gives us is spacetime curvature. So, what is it that general relativity gives us that we don't get yet from special relativity? The thing that can be unified fairly nicely with quantum mechanics via quantum field theory. Well, general relativity gives us the principle of equivalence, or I should say the principle of equivalence integrated with special relativity yields general relativity. The principle of equivalence is where the acceleration, that feeling where you are pushed back in your seat when you're accelerating in your car, that is entirely equivalent to the sensation of weight. The fact that you feel that like you weigh something when you're standing on the ground. Those two situations are entirely equivalent. Standing on the ground is equivalent to accelerating upwards from the center of the earth. And the acceleration is 1g. So the space-time curvature is organized on the left side of the Einstein gravitational field equation in terms of the Ricci tensor, which organizes the outputs of these functions in terms of curvature, with a factor, a correction factor, that is subtracted from it, that being the Ricci scalar, the scalar curvature. So, how to go ahead and bring this together with quantum mechanics and quantum field theory through the spacetime algebra? Well, one probable means of doing this is to vary the operator for the spacetime algebra, which is the metric for flat spacetime. When you construct a spacetime product, you are basically taking a dot product and a wedge product, adding them together, using the flat spacetime metric. Well, suppose that we introduce curvature to that metric, and to do that is not straightforward. We have to organize the components of the curvature using what I feel is going to be the Ricci tensor. And then I believe we're going to have to use multi-vector inputs, which also contain curvature type quantities. And then the output very likely will include, well, if it's a multi-vector, it's a high likelihood that part of the output is going to be the grade 4 part, which is the pseudoscalar. And of course, the pseudoscalar squares to -1. And the pseudoscalar, along with other parts of the multivector, can be used to construct complex scalars, such as what are used routinely in quantum mechanics, as well as complex vectors. When I think about a complex vector, I think of a spinner, also very prominently used in quantum field theory. especially that for fermions. But the other thing about the pseudoscalar is what it represents geometrically, and that is a 3+1 dimensional space. And that 3+1 dimensional space can also be a curved spacetime, allowing another means for curvature to access the Schrödinger equation. I think the setting where the spacetime curvature will play its most obvious role is when we are solving the Schrödinger equation in terms of a spherically symmetric solution. When we are generating a spherically symmetric solution. I mean, that's where the spin statistics comes in. That's where energy levels and orbitals come in, the structure of the atom. How does spacetime curvature modify this process? Or maybe another question is, how does this process actually cause curvature in spacetime? Whether it be a clock clicking at a relatively slower or faster rate, or dilating or contracting distances. How does the presence of a quantum state give rise to mass and to gravity? So, this is my latest update on the studies of really how to integrate gravity with quantum field theory.